Okay, I'm going to take you through the entire process of all of the things we have learned about how to use the derivative. So this is kind of like a summary for those of you that still are a little confused. So we start out with this function. A couple things to note. X cannot equal 2, and that's something that's important, especially for later on when we start to look at points being defined. So let's take the first derivative. And we're going to take the first derivative so we can find critical numbers. And this is the start of the first derivative test and the second derivative test both. So v u prime minus u v prime all over v squared. Now we need to simplify. I'm going to multiply this out. So I have 2x squared minus 2x minus 4x. That's minus 6x plus 4. And then be careful to distribute this negative on everything. And I would leave this, it's already in factored form, leave it in factored form. So the first derivative, 2x squared minus x squared is x squared. Minus 6 plus 2 is minus 4. 4 minus 4 is 0. X minus 2 squared. So the factored form of this will allow us to find our critical numbers. So critical numbers would be where the denominator is 0 and where the numerator is 0. So we have 3 of them. If you notice, one of them isn't at our undefined point, which means there's an asymptote. So it's not going to be a critical number. It might be a place where something changes. It's not a critical number. Okay, so if we're going to do the first derivative test, we need to test the intervals where these critical numbers happen. So negative infinity to 0, 0 to 2, 2 to 4, and 4 to infinity. And so I'm going to plug in a value into the first derivative to see if I get a positive or negative slope. And that's going to tell me if it's increasing or decreasing, and also whether or not I have maxes and mins. So make sure you plug it in the right place. So we're plugging into the derivative. So pick a number, -1. You plug it in either form, whichever is easier. That's 1 plus 4, that's 5. This is squared, so it's always positive. So we have increasing. I'm going to plug in 1 here. 1 minus 4 is negative, so that's negative. So I have a max. Plug in 3. 9 minus 12 is negative. 3 minus 2 is positive, so that's negative. So that is neither. That's probably a shelf, or that's where our asymptote is. And then I'm going to plug in 5. 25 minus 20 is positive. I know that's always positive. So we have a min here. So I have my intervals of increasing and decreasing. And I know there is a max at 0 and a min at 4. To find the y coordinates for those points, I go back up here and plug in to find f of 0. Well, f of 0 is -2. F of 4, 16 minus 8 is 8 plus 4 is 12. 12 over 2 is 6. So I know I have a max and a min. Those are relative max and min. If I want to verify those, this is where the second derivative test. You don't always need to do it, but sometimes this is the only option. If you know your critical numbers and you take the second derivative at your critical numbers, you can find out if you have maxes or mins. Well, first of all, I need the second derivative. So I'm going to go start out with my derivative. And I'm going to do the quotient rule again. So v u prime minus u v prime all over v squared. And so before I go any further, I can reduce, there's an x minus 2 in everything. So I'm going to take it out. Sorry, this should have been to the fourth. So I'm going to take that out, and that's to the third. And that's to the first. So I have this expression, which is 2x squared minus 4, that's minus 8x plus 8. And then I'm going to just, this is 2x squared, but there's a negative. So it's minus 2x squared, negative 8, but there's a minus, so that's plus 8x. And you see what happens is things clean up pretty nicely. All you're left with is 8 over x minus 2 cubed. Okay, so that is the second derivative. To use it for the second derivative test, I plug in numbers. So I plug in 0. F double prime of 0 is 8 over negative 8. So it is less than 0, which means it's concave down, which verifies that I have a max. If I plug in 2, it's undefined, which tells me I have a possible inflection point there. So I don't do anything. There's nothing I can do. If I plug in 4, get 8 over 2 to the third 8 is positive. All I need to know is positive or negative. Concave up, which verifies I have a min. Notice the difference between concave and increasing, decreasing. They do not mean the same thing. Something can be increasing and concave up, and it can be increasing and concave down. So the concavity has nothing to do with the slope there. Those are separate things. So what I did with the first and second derivative test is to verify extrema, and that is what those tests both do. Now, the other use of the second derivative test is to identify inflection points. And so I set up a table just like the increasing, decreasing table, and 2 is my only value there. So negative infinity to 2, 2 to infinity, and I test the second derivative on either side of those. So on the left side, if I plug in 1, I get a negative, so it's concave down. On the right side, I plug in 3, it's positive, it's concave up. So my inflection point would be at 2. However, we said there's no point there, so I know there's an asymptote. So at the asymptote, it changes inflection. So what do we know? Well, if we're going to make a sketch of this graph, when we go to sketch it, we know there's a max at 0, negative 2. We know there is a min at 4, 6. And those are relative. It's weird because this point's higher, but they're relative maxes and mins. I know there's an asymptote at 2. The function is increasing until 0. So something, and it's also concave down. So something like this. Okay. It's decreasing, and then it's still decreasing after 2. And then at 2, it's increasing. So I have a sketch of my graph without using a calculator. Now, if you want to verify it on a calculator, you just enter the function. I have a different window set, so I need to change my window and see what we have. Pretty good sketch of what it should look like. And there's something else here that you may have talked about in algebra. There's a slant asymptote as well, but you don't need to know how to find the slant asymptote. That's it.